recording. Hello and welcome to our fifth lecture together. This is Math 140 SCI Science, lecture number 5, September 14th. And we are starting, I should start sharing this. We are going to start on chapter 3 on what is called the normal distribution. So, chapter 3, the normal distribution. And the normal distribution is unquestionably the most important distribution in statistics. Of course, I keep using this term distribution, which we haven't really technically defined. So you might be a little justified in saying, I have no idea what you're talking about because you keep using this term distribution and you haven't defined it. And you'd be right. So let's go ahead and start section 3.1 on what are called density curves. And as we progress through this chapter and we learn about what a density curve is and what density functions are, we will understand what a distribution is, and then finally we will understand what the normal distribution is. Does anyone know from previous classes, either statistics or otherwise, that might have used some statistics, what the normal distribution is? Great, so you're going to learn a bunch of stuff today. So what I'm going to do here, I'm going to stop sharing there for a second. And I got a private message. I already answered that. Okay. So what I'm going to do here is I am going to load up a certain, let's see, I'm going to load up, it is central limit theorem applet. And I believe it's this first one that I want to use. Okay. So this, I'm not sharing my screen, am I? So let me share my screen. Okay. So this idea of the central limit theorem is something that we're going to get to later. I don't want to worry about what the central limit theorem is right now. I just want to highlight some features. Suppose, we're going to start with number 1 here. Okay, suppose I have a, let's say I ask you to pick a number from 0 to 100. And I tell you in advance that any number is as equally likely to be chosen as any other number. What this little picture here looks like is it's flat, which means the likelihood of 0 is the same as the likelihood of 1 or 2 or 3 all the way to 100. And suppose I pick at random a number, let's say 50,000 times. Do you expect in a realistic situation that I get exactly the same amount of each number every single time? Same number of each number every single time? Would you expect that to be the case, that if I do 50,000, I get exactly the same number every time? No, not exactly the same number, but it should be pretty close, right? Especially with a large sample like 50,000, correct? So I'm going to do it. I'm going to have it do it. I'm going to do a high population size, so like thousands upon thousands upon thousands, and let's see what happens. Every one of these is one of the options from 0 to 100, or maybe there's not enough bars, so maybe it's like a histogram where each one is like 2 or 3. I have 104,618 choices. My sample size is essentially a sample of 104,618. Does this seem realistic, a realistic outcome based upon a situation where every number is exactly equally likely as every other number? Does this seem like a realistic outcome with how many zeros and how many ones and how many twos and so on? Does that seem realistic? Yes or no? Is anyone there? Is everyone following what I'm talking about? Does this make sense? If I did it again, would I expect it to look exactly the same? Well, let's do it again. Let's see what happens if I do it again. Not exactly the same, but it is still fairly close, right? It still looks like it's representative of a situation where each number is equally likely. Here, the population was a different size. But again, I still have a situation where my histogram looks very similar to this. Do you agree? It'll be slightly different every time, right? Every time we do it, it's going to be a little bit different, but similar, correct? Now, what if I have a distribution that looks like number 2? That means the numbers on the far left are very unlikely to be chosen. The numbers on the far right are very likely to be chosen. And the numbers in the middle are somewhere in between. What do you think my histogram is going to look like if the underlying reality looks like number 2? What do you think my histogram shape would look like? Right? Someone said a slant, higher on the right. Well, let's take a look. Does this kind of conform with what we expect?
Yeah.
Yes, and there's some very strange looking shapes here. Like if I did number 4, like number 3, very likely to be a small number, somewhat likely to be a big number, but very unlikely to be a number in the middle. So if I did 100,000 runs, I probably get a lot of those, a bunch of those, and a few of these, right? And if I draw it, do I get something that's representative? And the answer again is, like all the other cases, the answer is yes, right? These shapes down here, these are what are called density curves or distributions. They are idealized drawings, idealized graphs that represent the true underlying scenario, where a histogram can only represent an actual case where I actually take values and I actually perform the experiment. If I actually perform the experiment, it's never going to be perfect. It's always going to have these little, variations, because that's reality. The density curves, on the other hand, those are the idealized perfection that I expect if my underlying model is correct. That's the difference between a density curve and the actual histogram. This one, number 5, as we're going to see today, has a special name. What is the name of this distribution, of this density curve? That looks like it's not a parabola. It's flat. It goes up, it peaks, it comes down. This is called a bell curve. Another name for a bell curve is a normal distribution. So this chapter on the normal distribution is the chapter on bell curves. Of course, the bell curve, the normal part of the chapter, isn't until we get a few sections in, but that is the goal of the chapter. In a later chapter, we're going to cover the actual central limit theorem itself. And when we get to the central limit theorem itself, we're going to come back to this applet and we're going to see what happens if I increase the sample size and how that affects things. But we're not there yet. This was the point of that little demonstration, is the difference between the density curve itself, which is the idealized model, and the histogram, which is what actually occurs. And if you have the book in front of you, in fact, you know what? Let me, just in case you don't, I will go and share again here. I'm going to load up the ebook so I can show you. And we're in chapter 3 now. So let me share my screen again. And we have in chapter 3 our density curves here. So we have another example of the situation. What we have there is a histogram. And this histogram is the actual results of a experiment performed where we were looking at, in this case, Iowa test vocabulary scores amongst 7th grade students. And the histogram tells us essentially the percentage that scored this over here between 0 and or between 2 and 3 and 3 and 4 and whatever the numbers are. The red curve is this idealized density curve. It's this graph that we draw that we feel is the underlying reality behind the situation, because the histogram is never going to be exactly perfect in terms of what the reality should be, because it's an experiment, and experiments are never perfect. If I were to go ahead and so here's essentially the same situation. We still have 2 to 12. This is the same graph, it looks like. It just says the vertical scale is adjusted so that the total area under the curve equals 1. So essentially what we did is if you think about it, if I add up all the percentages of all of the rectangles of my histogram, it has to add to 1 because every result had to go somewhere, correct? This is not a new concept. We've talked about this before. The rectangles have to add to 1, but my curve that I draw through them might not have an area underneath it equal to 1. But to be one of the 2 conditions necessary to be a valid density curve, as we're going to see in a few minutes, is that the total area under the curve has to equal 1. So this one was adjusted a little bit just to make sure that the total area under the curve has to be equal to 1. That is one of the 2 conditions to be a density curve. So with that said, let's now write down what a density curve is. Okay, I kind of gave you 2 different viewpoints on it, one from the book and one from the applet. So a density curve is a curve that, 2 conditions. One is always on or above the x-axis. And 2 has area exactly 1 underneath it. And each of these 2 has a reason behind it. Why do you feel, let's do the first one. Why do you feel a density curve has to always be on or above the x-axis? Or if you don't want to answer that one, why do you feel that a density curve has to have an area of 1 exactly underneath it? Give me a reason why you feel either one of those should be a true statement. Anyone have an idea? So remember what the histogram represents. Those rectangles represent the likelihood of landing inside that range of that number to that number, correct? If my rectangle has a height of, let's say, 12%, then I'd say that there's a 12% chance that I land between here and here. Well, if the rectangle goes beneath the x-axis, that's essentially the equivalent of saying that there's a negative chance that something happens. How can you have a negative likelihood of occurrence? What's the smallest possibility? 0. If it can't occur, 0. If it definitely occurs, 100%. You can't go negative. So the reason why the density curve can't be beneath the x-axis, because that would imply a negative likelihood of occurrence. And that just does not make any sense. So the first one, right, the first one is the density curve. The density curve represents probabilities, represents probabilities or likelihoods which cannot be negative. That's why the worst that can happen is it's on the x-axis to represent that it can't occur, 0%, but it can't be less than negative, less than 0. How about having an area exactly equal to 1? What's the reason why the area should be exactly equal to 1? Well, again, if you add up all the rectangles, it has to add to 100% because every outcome has to be somewhere. If the density curve is the underlying reality for which the histogram is an approximation, then the area under the curve is basically the sum of the rectangles. And if the sum of the rectangles has to be 1, then the area of the curve under the curve has to be 1. So the area under the curve has to be 1 because the area represents all possible outcomes with their corresponding probabilities. Which must add to 100%, which must add to 1. So if you have a curve and someone says, I think this is a density curve. And you say, okay, well, let me check 2 things. 1, let me check that it never goes negative. And 2, let me check that the area underneath it is equal to 1. Now, that's a little easier said than done. Because how exactly do you find the area under a curve? If the curve is a rectangle, like our first example on that applet, right? If I make a curve like this, finding the area under it is pretty easy because it's a rectangle. What's the area of a rectangle? Anybody? What's the area of a rectangle?
Times width.
Length times width, base times height, L times W, right? We know the area of a rectangle. But if I have this bell curve shape, how exactly do I find the area underneath that? And the answer is calculus. Calculus has 2 main objectives, and one of those objectives is area under curves. That's actually calculus 2. So you have to get through calculus 1, which is the other objective, before you can get to calculus 2. But once you do, you learn about ways of finding areas under the curves. Has anyone here taken calculus or plans on taking calculus? Or had a dream about taking calculus? Or know someone who took calculus? Or has heard the word calculus? Or, okay, you've heard the word, good. So, fantastic. Anyways, that's a part of what calculus does. Of course, it does a lot. You took pre-calc. Thank you, that does nothing. But thank you anyways for your contribution. It's always nice to hear everything. I took it in high school, loved it. I finished differential calculus, amazing. Calculus AB, this is great. So you've seen some integrals, right? Some area under curves, correct? Fantastic, amazing. So some of you know what I'm talking about. I love it, I love it. Well, there's a lot more than what you've learned in AP Calc. It goes much beyond that, it's fantastic. Anyways, this is the idea of density curves. Are there any questions on section 3.1? Because that really is it for section 3.1, density curves. It's just more of a conceptual than a mathematical idea. So now let's move on to section 3.2 on describing density curves. And we already know how to describe density curves. You know why? Because we already know how to describe histograms. And density curves are essentially idealized histograms. So if I have a density curve that looks like this, a nice bell curve, what would I call this? What shape would this have?
Symmetric.
This is symmetric. And where is the mean located?
In the middle.
In the middle. And where's the median located?
In the middle.
In the middle, because the middle point for a symmetric graph is the halfway point, and it's also the balance point. What if I had a distribution or a density curve that looked like that? How would I describe this density curve?
Right.
This is skewed to the right or right skewed. And where are the mean and median for this type of density curve? I'll draw again the peak. So where's the mean and median? Oh, why did I say mean and middle? That doesn't make any sense. Mean and median. Thank you all for correcting me. Okay, mean and median. So for the right skewed graph, where is the mean located and where is the median located?
The median is a little more towards the right, and then the mean is more than the median.
Excellent. They're both pulled to the right. The median, not so much, because it's a resistant measure, and the median more so, because it is a non-resistant measure. And it's kind of hard to visualize exactly where the median and mean are located, but generically, the median is pulled a little bit to the left, and the mean is going to be pulled more to the left. And if it's a left skewed graph, with the peak being here. By the way, where's the mode for this, for the original graph? Where's the mode? Of course, we have to understand what mode means here, because a mode, we've always interpreted a mode as the outcome that occurs the most often. But we're not actually performing an experiment. There's no histogram here, right? There's only an idealized underlying model. So where should the mode be on this idealized underlying model? You can't say it's the one that occurred the most often, because nothing occurred the most often. I didn't do an experiment. So where do you think the mode should be?
Would it be like the peak?
It should be the peak. It is the one that is most likely to occur. So the mode is the peak. Can't say it's the one that occurred the most because nothing occurred, but it's the one at the peak. Okay, and where is the mean and median for this left skewed density curve? Where would the mean be and where would the median be?
The median would be a little bit from the mode, and then the mean would be even more.
Which side, right or left?
Left.
Okay, so the median is pulled slightly and the mean is pulled more so. So it's very similar to the way we described histograms, but again, let's remember that there was no actual experiments performed. So we have no middle value. We have no most often value. We have no average of values. But rather what we're saying is, if this was the perfect histogram, then this is where the mode would be, this is where the mean would be, and this is where the median would be. So it looks very much like histograms, but conceptually it's different. Okay, are there any questions on that so far? Going once, going twice, sold. Okay, so 3.3 on the normal distribution. Okay, 3.3 on the normal distribution. Is that perfect? Okay. All right. So first, let's define what the normal distribution is. So a distribution is a probability model that is described by a density curve. So when we talk about a distribution, we're basically saying, if I give you a density curve, i.e. the area underneath it is 1 and it's never negative, then that is representing a distribution of a distribution. And it can be the normal distribution, the geometric, the chi-square, the Poisson, the hypergeometric, the negative binomial, the student's t. There's all these different names as you go through statistics for different distributions, and they're basically models described by density curves. In some sense, density curves and distributions are almost synonymous because one automatically comes with the other. So if you have a density curve, you have a distribution. If you have a distribution, you have a density curve. They come one and the same. The normal is a very specific one. The normal looks, here's your horizontal axis, and the normal curve looks like that. It goes forever in both directions, but it approaches 0 pretty quickly because the area underneath it has to be 1. So you might say, how can a curve that goes on forever in both directions have a finite area underneath it? Well, again, this is calculus. It can. Let's just move on. The area underneath it is equal to 1. So what are some features of the normal? Some features of the normal. 1, it is symmetric. Every normal distribution, every normal is symmetric. It is single peaked, and it is bell shaped. Two, every normal, well, I'm not going to say every normal, but completely determined by 2 parameters. In other words, there are infinitely many normals, but every one of them is uniquely and completely determined by providing me with 2 pieces of information. Can anyone guess what one or the other of those 2 pieces of information might be for me to know which normal curve you're talking about? In other words, if you come along and say, I got this normal, I'm like, which one? And you go, oh, okay. Well, it has this and it has this. Oh, okay, that one. I need 2 pieces of information that completely determine which normal you're talking about. Even if you don't know, take a guess. Take an educated guess. Don't say like banana. That doesn't make any sense. That's an uneducated guess. Okay, but take an educated guess as to one or the other of the 2 pieces of information. What does the last word say after 2? Parameters. Here, I will use my 2nd grade best penmanship award spelling or writing. Oh, that didn't work. Parameters. It's the highlight of my life, winning best penmanship in 2nd grade. Don't take that from me. Don't you dare. Anyways, so completely determined by 2 parameters, 2 numbers, physical numbers. You can't just say 7 and 3. I mean, yes, technically 7 and 3 would describe it. But then I would ask, what's the 7? What's the 3? Someone take a guess.
Would
Be
it
the
one of them
mean
be the
one.
number at the top of the peak?
I'm sorry, hold on. I heard a couple things. Say again what you said.
Would it be the number at the top of the peak?
So the number at the top of the peak could be used, but it's not one of the ones that we're going to use. But it could be. Okay, so someone just did it in the chat. The first one is the mean. I want to know where this is centered. Is it centered at 0, centered at 10, centered at 100? Where is the mean located? Where is the peak located? So the first one is the mean, which is denoted by the Greek letter mu, also the sound that a French cow makes, mu. And we're going to be using that symbol a lot. That is the mean, i.e., it's where the center is. So the first piece of information is, where is it centered? Where is the center of the normal? But even if it's centered at the same location, right, I can draw different normals that have the same center. So what separates one normal from another? How spread out your graph is. In other words, the second one is the standard deviation. So the mean and the standard deviation, which is denoted by the Greek letter sigma, lowercase sigma, not the capital sigma. So Flower, you had said, is it the lowest point and the highest point? Well, the lowest point doesn't exist because it keeps getting lower and lower and lower, approaching the x-axis but never getting there. And Leanne said the highest point as well, but again, it wasn't. So good guess. I love guesses, even if they're wrong. The two things you need to completely determine which normal you're talking about are the mean, which tells you where the center is located, and the standard deviation, which essentially tells you how spread out the data is. The question is, by looking at this graph, can you just tell me, just by looking, how far I got to go from the mean? Do I go this far, or this far, or that far, or that far? How far do I got to go from the mean to go exactly one standard deviation away from the mean? How far? Do I go to this point? Is that one standard deviation? Or there, or there, or there, or there, or there? How far from the mean do I have to go before I can say that I've gone one standard deviation? Does anyone know the answer to this question? And if the answer is no, that's great. You're all going to learn something, or at least those of you paying attention, which might not be everyone. I don't really know. So going once, going 35%. 35% of what? Or 25%. 25% of what? I'm looking for an actual physical distance. Of the area. So it's not 25% and it's not 35%. So I'm going to do it to you right now. Show it to you right now. So look at the center of the graph. Just the center portion of the graph, the curve itself. Would you say that the center of the graph looks more like a bowl or like a hill? If you were to give it a characteristic, would it look more like a bowl, like you're eating cereal, or like a hill, like Jack and Jill? Okay, so it looks like a hill, correct? The center looks very hill-like. Do you agree? Okay, now, the edges of the graph. If you had to give the edges of the graph a characteristic, would you say they look more like a bowl or more like a hill? Or a portion of a bowl or a portion of a hill. So the edges are more like a bowl. Like they don't obviously go up again, but it looks more like a bowl, a half bowl at least, than the top, which certainly looks more like a hill. Does that make sense? That characteristic, once you see it, of course. Does that make sense? So I would like you, please, to tell me the exact spot. Now, we are doing it by eye here, so it's not going to be perfect. But tell me the exact spot on the graph where it changes from being more like a hill to more like a bowl. I'll give you some options. A, B, C, D, E, F, G, H, I, or J. Right? A, B, C, D, E, F, G, H, I, or J. Which letter, and again, this is only, we're only eyeing this, so we all might not agree necessarily, but which letter amongst those would you say is most likely the exact spot where it changes from being more hilly to being more bowl-y? And those are words that I just invented, at least bowl-y. So let's see what we have. We have an F, G, F, G, F, E, G, 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 D, I, G, G, E, and a B, actually. E, D's, F, G, H's. So first of all, you can see that just using your eyes to do this, a lot of disagreement. Even though mathematically, there's a mathematical formula that can get it for us, which means there should be no disagreement, which just lends credence to the fact that doing things by eye is not always easy. But if I had to pick a spot, I'd probably say somewhere in the vicinity of about there, which I think was like roughly E-ish or so. Even if you didn't agree with the exact spot, am I at least close to what you would pick? Is there anyone who's thinking like it's way further? Someone said B. I know that B was over here, but this is still kind of downwards versus upwards. So B is certainly not correct, but I think about that point would be roughly in the right area. This distance from the mean to that point, this distance is 1 standard deviation. So if I go to the point where the graph changes from being hill-y to bowl-y in either direction, I will have gone 1 standard deviation. And for those of you who had calculus, maybe you know what the definition of this point is. Do you have any recollection of what the technical term for any of this stuff is that I'm talking about? Those of you from calculus, the difference between the center and the edges. Anyone? There are only a few of you who have done calculus, but I'm just wondering if you guys remember what this was. Either they are not here or they are just, point of inflection. Look at you. Point of inflection. It's a very specific mathematical definition, and it's the point where the graph changes from being like a hill, which is what we call concave down, to like a bowl, which is more concave up. So the point where the graph changes from concave down to concave up, and these are not terms that you have to worry about in this class. These are calculus terms. But that is the point of inflection, and that is where how far you have to travel before you have traveled 1 standard deviation. Now, next question. If I go 1 standard deviation either direction, I will have covered, or I will have under the curve some of the total area, not the entire total area, because I don't have the whole graph here, but I have some of the total of the area. How much of the total area under the curve is yellowed in this graph? Now, if you already know the answer to this, don't say it, because then you're just saying something that you've seen before. But if you legitimately have never seen this before, take a guess as to what percentage of the total area falls 1 deviation from the mean in either direction. Take a guess. Even if it's wrong, just an approximate. Would you say it's half? Would you say it's less than half? Would you say it's more than half? If it is less than half, give me a better approximation. If it's more than half, give me a better approximation. 75%. That's a guess. So anyone want to guess something else? Approximately what percent of the data is yellowed in? What percent of the graph is yellowed in? I have one guess at 75%. That's so far the best guess. Okay, I have more than half. I have 80. I have someone says 50. A couple people said 50. Okay, 70, 60, 60, 80, 75.5. I feel like we're playing, what's that game where you got to go like over, but you can't go too much. So you go one more and you really screwed the guy before you. What's that game called?
Is that The Price is Right?
Oh, yeah, The Price is Right. That's right. Yeah, The Price is Wrong, everyone. Okay, so none of you got it, but some of you are pretty close. The answer is, and this is, but some of you were really close. Whoops, really, really close. Approximately 68%. Some of you were really close. I think I saw 65.5. I think 70 was the closest. All right, I think 70 was the best. Where's my chat? 675, 60, 75.5. I saw 70. Yeah, Alexis, 70. You go, girl. That's what I'm talking about. So approximately 68% of the total area is within one standard deviation, one sigma of the mean. Now, if I would have gone 2 sigmas from the mean in either direction, then I will, of course, cover more than 68%, correct? So I want guesses again for what percent of the graph would be 2 sigmas of the mean. And I'm going to stop there because someone already got it. The answer is 95% of the total area is within 2 sigma of the mean. And what if I would have gone 3 sigmas from the mean? I'm not going to draw it because I don't have enough room. But if I would have gone 3 sigmas from the mean, approximately what percent do you think would be shaded? Well, it's not 100 because the graph goes on. Also, Cynthia, you knew the answer, didn't you? Nobody would have guessed that without knowing the answer. But maybe you did. I don't know. I don't assume. But 99.7% of the total area is within 3 sigmas of the mean. Now, there's a law in probability, and it is called the 68, 95, 99.7 rule. Can anyone guess what the 68, 95, 99.7 rule says? I know this is going to be a tough one, but can anyone guess what the 68, 95, 99.7 rule says? Anyone?
From what I saw so far, I can see that like maybe 68 to 95 is one standard deviation, and from 95 to, or
Be very careful. It's not 68 to 95, that's 1. 68 is 1.
right.
If I go 1 sigma both ways, that's 68. If I go 2, that's 95. If I go 3, that's 99.7. But the numbers are not connected. 1 sigma, 68. 2 sigmas, 95. 3 sigmas, 99.7. The 68, 95, 99.7 rule is just that. This here is to 68, 95, 99 point for a normal distribution. This is all normal. This is all normal. If I didn't explicitly mention that, I should. This is all specifically for the normal. It's not true for other cases. Okay, this only holds for a normal distribution. This only holds for a normal distribution. There is something that holds for other cases, and we're not going to do it. So it's more complicated. But this, if anyone wants to know what it is, you're more than welcome to stay after I can describe it. But it certainly is more complicated. So this only holds for a normal distribution, okay? So what other pieces of information do we have? Let's see, the mean is at the center, which I know I put on the graph, but I should specifically say that. The mean is at the center. The mean and median and mode all agree. And I don't mean they agree with each other like, hey, yeah, I agree, you're right. But I mean, they all say the same thing. Yeah. So these are the properties. And I should say, 1 sigma, symmetric I said, that's the very first thing I said right there. 1 sigma is the distance from the mean to, I'm just going to say the point of inflection, because that's what I labeled in the graph. And even without knowing how to calculate a point of inflection, you can still see on my picture the point of inflection. Any questions so far? All good so far? Going once, going twice. Okay, going 3 times.
I had a question.
Yeah, go ahead.
What did the 2 standard deviation look like again on the graph on the?
Oh, that's just traveling twice as far,
Okay.
right? If you travel 1 sigma, you get to here. If you travel 2 sigmas, you get twice as far. And if you travel 3 sigmas, you get 3 times as far. And 4 sigmas, 4 times as far, and so on. Anyone know of any very famous normal distribution situations out there in the world that are described by a normal distribution? Anyone know one of any? IQ, yes, that's a very famous one. What is the mean for IQ? What is the average IQ score? If you know the answer to this, you didn't know there was IQ, but do you know the mean? I'm sure this particular one will pop up via examples as we go through the book, but the mean for the IQ, the average IQ is 100. And the standard deviation is 15. So what does that mean? Let's translate that into context. So here's an example. IQ is normally distributed, or IQ scores or whatever are normally distributed with a mean of 100 and a sigma of 15. So question, what percent of people score between 85 and 115? What percent of people score between 85 and 115? So the answer is 68%. Because if you draw a normal curve whose mean is 100, and you go from the center, whoops, let's move that over a little bit. If you go from the center, which is 100, and you go to 115 or 85, which is 1 sigma to the left and 1 sigma to the right, then we know that the area underneath the curve is 68% of the total area, correct? But what is the total area under the curve? What's rule number 2 of being a density curve? What's the total area under the curve? It's got to be 100%. So if the yellow shaded part is 68% of the total area under the curve, the yellow part must represent 68% of the area, or just 68%, correct? So which means from 85 to 115 is approximately 68% of scores. Yes, no, maybe so? Have a harder question. What percent is between 100 and 130? And don't just say the answer if you see it, because I want to give people the chance to think about it. But what percent of IQ scores will be between 100 and 130? I want you to think about this. You can draw whatever you want to draw, make pictures, label things. I want you to look at what we've covered so far. I'm going to give you guys a minute or two, and then I'm going to ask, like we did before, for a nice, quick, everyone posting their answer at the same time. I kind of like it. It's fun. It gives people the chance to write their answer down with a lot of others, so that if it's wrong, nobody notices. And you also can really see if you understand what's going on, rather than just copying someone else's work. Oh, why? After all I just said, why? Write the answer. Oh. Cynthia, can you hear me? Sorry, that wasn't I don't think that's English, but I accept your apology. So, can you explain, Cynthia, since you said the answer, why it's 47.5?
Can you hear me?
I can.
Sorry. So I did, because from 100 to 115, that's one standard deviation.
Okay.
So 100 to 130, that's 2 standard deviations. So I know that 2 standard deviations, but from like the left and right of the mean is 95%, but we're only doing half of the mean, like half of that side. So we do 95 divided by 2.
That
You
was
get 47.
a wonderful explanation. All right, we know that if you go 2 sigmas in either direction, that's going to add to 95%, because that's the 68, 95, 99.7 rule. But we're not going in both directions. We're only going in one direction. Which means, by symmetry, since the left side and the right side look the same, if the entire is 95, then from 100 to 130 would be 47.5%. Does that make sense? So let's try it again, and this time no akakakang, please. Let's do the following question. What percent is less than 115? So the answer to this was 47.5. Okay, without spoiling, I want everyone to think about it. What percent is less than 115? And I'm going to give you a couple minutes, and then we're going to try again. Okay, so on the count of 3,000, just kidding, on the count of 5, I would like everyone to write down and then hit enter after I say 5, what they believe the percent that is less than 115 is. 1, 2, 3, 4, 5, go. That's 3 people. I'm looking for the everyone that I was kind of hoping for. Where's everyone else? We got like 40 people in here. Spoiler alert, those 3 people were all wrong. So if you're embarrassed about being wrong, shouldn't be. Still wrong. Still wrong. Come on. Come on, see what you got. 83.85. 83.85. That seems like it might be a calculator computation because that's quite accurate. It's not what I'm looking for, but you know what? Let me get out my calculator and see what my calculator says. Let's see. And we're going to learn how to do this on a calculator eventually, but not there yet. So hold on. No, that is not correct. 81 is not correct. So 88.5, not correct. This is good. I like all these wrong answers because it means that you have something to learn, and you're only going to know if you have something to learn if you give it a shot. If you don't do anything and you wait for me to give the answer and then you say, oh yeah, that makes sense, I get it. You don't really learn as much because you think, oh, I would have gotten that. You'll really know if you would have gotten it, if you write something, 99.7 is not correct. No, that can't be right. You're missing all of this. It's going to be that only 0.3%. No, that can't be right. 65 is not correct. 25 is certainly not correct. 75 is not correct. Okay, I love all these answers. They're all wrong, but I love them all. 91.75 still not correct. 78.5 still not correct. 84.7 is not correct. Close, but not correct. The answer is, at least for us, without the calculator that can do better. No, someone already said 83.85. That's not correct. The answer that we're going to have today is 84%. And if you're thinking that 83.85 was what I'm rounding from, it's not. I'm actually rounding from that. Which we're going to learn later how I got that. But for now, here's how I got it. Question. Let's go to green. How much currently is shaded in the yellow?
68.
68%. So if I focus only on this half of the yellow, how much is that?
34.
34%. Now, the left half of the curve is exactly how much?
50%.
50%. It's exactly half. So between them, I get how much? %84. Does that make sense?
Where's the 30% from again?
30? What 30?
Whatever is written on the left side.
Oh, 50. Right? The 50? That's half that's half of the bell curve.
Sorry, it looked like a 3.
Sorry. Everything to the left of center is exactly half because everything to the right of center is exactly half. It's symmetric. The center divides it perfectly on the middle. 50% to the left, 34% on that little part on the right. How much in total? How do I get 34%? So again, barely, the yellow part is how much?
68.
Okay, well, this is half the yellow. Right? The yellow goes from 85 to 115. We want 100 to 115. That's exactly half of the yellow, correct? Yes, no, maybe so? Yeah. So let's do another example. Let's do another example. Example. Suppose we have a situation. So we have a normal situation, a normal distribution. Okay, gotta be told that it's normal. Mu, and I don't even care what the context is, although every problem that you do will have a specific context. What exactly are we measuring? But numerically, we can do it without worrying about that right now. Suppose we have a situation where the mean is 6.84 and the standard deviation is 1.55. Okay, so we have a normal distribution with these parameters. And remember what I said before, mu and sigma, the mean and deviation, are all you need to uniquely determine the distribution. So between normal, mu, and sigma, I know what I'm talking about. I should be able to calculate everything. In fact, here's the question. Let's do this one. What percent let's take a look. What percent are between 3.74 and 8.39? What percent are between 3.74 and 8.39? I would like you to take a couple minutes to think about this. I recommend drawing a normal curve. I recommend labeling things. I recommend shading things. I recommend thinking. You'll need all of those. Well, you don't need all of those, but I recommend using all of those to see if you can figure out the answer to this question. And I'm going to do it right now as well. Okay. I believe I have the answer. Don't say the answer if you think you have it. I'm just curious. Just say in chat that you believe you have the answer. Or I think I have the answer, or I might have the answer once you believe you have the answer. Okay. If you want to direct message, for those of you who think you have the answer, go ahead and direct message me what you believe the answer is. Or secret, whatever it's called. How do you? Okay, Stephanie, that's close, but not quite. Luis, close, but not quite. Mary, that is correct. Nikki, that is correct. Sheila, close, but not quite. Luis Govia, that is correct. Alexis, close, but not quite. So that's great that a few of you did get it. I have 3 people who got it. Leanne, that is correct. Oh, look at that smile. Yeah. Feels good, huh? Jason, that's correct. We'll go over this one, Flower. Remember the rule, the 68, 95, 99.7 rule. Okay, so here I'll go through it. Here's the first thing I'm going to do is draw my normal curve, or at least my best facsimile of my normal curve. The peak I will label as what? Cynthia, close but not quite. The peak I will label as what? Stephanie, that is correct. Although I think when you first, oh, you corrected it, Stephanie. Your first was wrong, but this was correct. Very good. So the peak is 6.84 because it's the mean. Correct? Now, if I go 1 sigma to the right, what do I get up to? If I go 1 deviation to the right, where am I at? Oh, 8.39. Well, that's the second number. Good, that's the bound. I don't got to go any further because that's what I was looking for. What if I go 1 to the left? What am I at there? 5.29. Okay, well, I'm not quite there yet. What if I go another one to the left? What am I at now? Oh, 3.74. Okay, good. So those numbers are really nice because they're right exactly at bounds. And this is not straight at all, so let's fix that. Okay, so the question now becomes, what is the area between these guys? Well, let's do the following. First, if I were to go 2 deviations in both directions, what percent would be in that entire area? 95%, which means the left half of that is how much? 47.5%. Now, if I were to go 1 deviation in both directions from the mean, what percent is that? That's 68%, which means if I were to take half of that, what would that be? 34%. Well, I just shaded everything I needed. I have this 47.5 and this 34. for a total of it's quite anticlimactic with nobody writing it, but the total is 81.5%. So 81.5% will be between 3.74 and 8.39. Flower, did I answer that question of yours? Okay, are there any questions on how this works? All right, so we will eventually, by eventually I mean Thursday, most likely, show how to use the calculator or tables or crunch it to compute these kind of things. Can you show the whole problem again real quick? You mean including the questions like that? Or do you mean you want me to explain it? Oh, okay, just want the questions, okay. Are the 68%, and yes, they are constants. These are numbers that never change. The 68, 95, 99.7 rule is for the normal, every normal distribution in existence. Now, granted, it's not exactly 68%. It's not exactly 95%. It's not exactly 99.7%. Those are approximations. Your calculator will do slightly better approximations. Crunch it will do slightly better approximations. But for a quick back of the envelope calculation per se, where you're just scribbling a little bit to get an answer, these are the numbers that we're going to use for the normal distribution. How come in the previous problem? Well, because in the previous problem, Andy, we were going all the way to the ends. We were doing everything to the left, including this part here. And when I include that part there, that's 50%. But in this case, I was not going all the way to the end. I was only going to there. And that is only 47.5%. Does that make sense? So we're gonna have you're gonna have lots of these examples of calculating normal probabilities, normal areas, and you're gonna be using the 68, 95, 99.7 rule. Now, what if I gave you I'm not gonna do this right now, but just to illustrate, what if I said, how about for the same problem, between, I don't know, 5 and 6. What if I said between 5 and 6 for the same problem? Well, here we have issues. What's the issue that we have if I ask you for this between 5 and 6? All the stuff that we learned so far, how would that avail you to solve this problem? Everything we did so far required you to be exactly at the center at 1 sigma, 2 sigmas, 3 sigmas, and so on. You can't just pick numbers in between and say, I got this, no problem. I'll just make this change or that change, or I'll do this instead. No, the 68, 95, 99.7 are 1 sigma, 2 sigma, 3 sigma only. 5 and 6, oh, 5's over here somewhere. 6 is over here somewhere. How in the world would I calculate the probability of being between 5 and 6? I can guess, but I don't want to guess. I want actual numbers, right? But even with decimals, it's still guessing. There's the 68, 95, 99.7 rule does not work if you don't land on exact sigmas. If you land on numbers in the middle of nowhere, this rule fails completely, which means we need some slightly more sophisticated techniques for answering it. And we start by considering section 3.5, the standard normal distribution. How many numbers are required to uniquely determine which normal distribution we're talking about? What two things must you give me for me to know which normal we're talking about?
Standard deviation and the mean.
Yes, the mean and the standard deviation. There are infinitely many choices for the mean. There are infinitely many choices for the standard deviation. The standard normal has a very specific mean and a very specific standard deviation. If you were to take a guess at a very convenient number for the mean, for the average, that you think would be easy to do math with and make problems easier to solve, what is a very convenient specific number to pick for the mean that you think might make your life a little bit easier?
1,
1 is good, 50 is good. I can think of one that's even better than all of those, or both of those.
0,
0. Have your normal centered at 0. It's a really convenient choice to make. But we still have to have some spread. You can't have a normal that doesn't have any spread. It has to spread out. So we also want a nice sigma that will make our life a little easier. Can you think of a nice sigma? And the answer is 1. Correct. The standard normal distribution is one of the infinitely many that you might find that specifically has a mean of 0 and a sigma of 1. It is called the standard normal distribution. And while a generic normal is usually denoted by the letter X, X equals 3.74 or 5.29, 6.84, and so on, those problem numbers from the previous problem. The standard normal is denoted by a different letter. Can anyone guess? Well, you wouldn't guess it if you didn't know it, but does anyone know the letter that we use for the standard normal distribution? If you don't know it, I mean, you have 1 in 26 chance, so you might guess it, but it's not S. So it's a good guess. It's not S. And it's not N either. It is. Come on, everyone just throw out a letter. Let's see if anyone can guess it off the top. Let's take a look. If anyone can just guess it. Z. I don't know if you knew that or you were guessing it, but it is Z. The standard normal is represented by Z. And what's really, really, really awesome is that we can turn any normal into a standard normal. Why is this convenient? Because imagine the days before calculators and before computers when you had tables to actually calculate values. Can you imagine having tables for every single normal possibility? There's infinitely many of them. How would you have tables for every scenario? But with the standard normal, you only need one table because you can turn any other normal into the standard normal. And once you do that, you have one table that can solve everything. Your calculator, you don't have to convert it to the standard normal, but you could. Crunch it, you don't have to, but you could. With tables, you have to. There's no way around it because there's not a table for every scenario. So how do I take a generic normal and convert it to a standard normal? The answer is by the following formula. Z equals X minus mu over sigma. And I want to demonstrate this with the following example. And by the way, this thing here is called a z-score. This guy here is your raw data. So you take your actual data, you subtract the mean and divide by the standard deviation, and you now have your z-score. So let's do the following example. It says the heights of women aged 20 to 29 in the United States are approximately normal with a mu of 64.1 inches and a deviation of 3.7 inches. Suppose a woman is 70 inches tall. Oh, not a question. Suppose a woman is 70 inches tall. Is that abnormally tall or not? Is this, I won't say abnormal, it's probably a bad word to use, but is this strange? What do I mean by strange? Well, if you look at a normal curve, where are most of the outcomes likely to be? Where are most outcomes likely to be if you have a normal situation? In the middle, near the center, the middle 68%, right? So that's what we assume the most. If you are more than 2 deviations away from the center, it's considered a strange result. It doesn't mean you're strange. You might be. I'm not taking a abnormal. I mean, yeah. But I didn't want to make it seem like this was like a deficiency of some kind, a defect to be 70 inches tall. But the question is somebody 70 inches tall? Is it strange? Well, what we're going to do is we're going to compute the z-score. What is this person's z-score? Well, we take her raw data, which is 70. We subtract her mean, which is 64.1. Unique. Well, but it's not unique because there's others like that as well. She wouldn't be the only 70-inch person in the world. So I can't say unique, but different. How's different? I don't know. So 70 minus 64.1 divided by 3.7. Let's see what our calculators give us for this one. 70 minus 64.1, and we divide that by 3.7. What do we get? Approximately, what do we get? Whoa there, buddy. I don't think so. 1.59. I'm not sure where 52.67 came from. Hold on, I'm trying something. I see where it came from. You got to do 70 minus 64.1 in parentheses because you want to divide the entire subtraction by 3.7. If you leave out the parentheses, then what you're doing is 70 minus 64.1 divided by 3.7. 70 minus that number, and that would give you 52.67. So, or 0.68. Okay, but make sure you don't make that mistake because it's a bad mistake to make. So here's our answer. The z is 1.59. Is it strange to be 70 inches tall or not? Well, let's draw the normal curve for the standard normal. What number is the mean? No, that's for the original normal. I'm talking about the standard normal. What's the mean of the standard normal distribution? Not the original, not the raw data situation, the standard normal. What's the mean of that one? 0. What's the sigma for that one? 1. which means 2 sigmas is 2. Where did the 70-inch tall woman land?
1.59.
1.59. Is that strange? No, it's within 2 dBA. Yeah, I saw you, Leanne. You can't just nod your head and then switch. No, I can't do that. That's the risk of being on camera. You can't hide that. So if you're within 2 deviations of the mean, this is not considered, well, it's not the greatest graph either, but it's not considered strange. So a 70-inch tall woman, that's just 1.59 deviations above the mean. This is the beauty of the Z-score. I don't care what your actual data is. I don't care what your actual mean is. I don't care what your actual sigma is. Because what I'm going to do is I'm just going to compute how far you are from your mean in terms of sigmas. You are 1.59 sigmas above the mean. And 1.59 sigmas above the mean is not strange. So your Z-score tells you how many of your sigmas you are away from the mean. Does that make sense? We will pick up here next time and certainly do more examples, because this whole chapter is on the normal and we're going to need this for the entire course. Everything we do, for the most part, from here on out, relies upon the normal distribution. Even sometimes when we don't realize it is, it's happening behind the scenes. But we need this stuff down cold. So we are going to spend another full day on it and make sure by the end of this week that we have this stuff down. All right? Again, the mini quiz will open tonight at midnight. And you'll have till midnight tomorrow to do it. There's homeworks, there's other stuff going on. Don't fall behind. You guys are awesome, some of you at least. And I'll see you guys on Thursday.
Thank you.